Hello. Um, in the previous video, I explained the intuition behind MLE. Here we are coming back to the slides, the original slides by the textbook, and let's think about what happens to the OLS. If you use the OLS like we use, the OLS was this when you use the linear regression model. But now we have nonlinear function here. As I said, the idea of the least squares method is that we interpret this as the prediction error, and so we square that and sum that. So squared error is the size of the residual, the prediction error. So you sum all the errors and you minimize that. However, in the probing model example, or in the binary dependent variable cases, it does not make much sense. So for example, I think earlier I did not do a good job in explaining this. Suppose that your problem is that, say, I'm wondering what is the probability that Tom Brady wins the Super Bowl last season, say, before the last season. What is the probability that Tom Brady wins the Super Bowl? And it in the end, it happened. It was true. It is realized. But the problem is, before the season, even if you are a big fan of Tom Brady, say, suppose that you predicted the probability to be 80%, which means you did really well. 80%, probability 80% is very good, but still you have 20% difference. So in any case, you cannot get to the 0 or 1 in the model. So the residual means nothing. And another problem here is, so 80% is good enough. But 90% would be better, of course. But the problem there is, like from 50% to 51%, the difference is equally 1% point, but it is not much of a difference. But in the end, 99% and 98% should be a huge difference. Still, the 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 difference is only 1% point, which is the same as 50 and 51, which is unfair. So this least squares summing up the errors is not appropriate for probability predictions. So it is not wrong, but it is not natural. So it is not widely used. It's not actually used in practice because we have MLE, and maybe the only problem of the MLE is its computational burden. But these days, computational burden is not a concern. There, uh, Stata does it for you, and it's just a matter of your memory. Uh, so your CPU, if your computer has uh, good enough CPU and memories, then MLE is always better than the least squares method. That's why it is not used. And coming back to the MLE, the likelihood function is, so it explains the likelihood function in a more complicated, more formal way. Likelihood function is the conditional density of the outcome given the information, treated as a function of the unknown parameters beta 0 and beta 1. Exactly, this is the formal statement of what I tried to give you earlier. Uh, and we maximize that. Okay, that makes sense. Uh, and in uh, and in the large samples, the MLE has many nice properties. It is consistent. It is normally distributed. It is efficient, which means the variance is the smallest. I mean, the standard error is the smallest of all possible of all or regular estimators. So it's a big deal. It's a very, very good. It means it's the most accurate estimator among all consistent estimators. That is a very powerful result. And here it considers a special case with no information, no prior information available. Then it is like coin toss. You are tossing a coin many times, let's say 100 times, and you are predicting the probability of heads. And of course, each time the probability is the same, so you repeat the same game 100 times. Say data is head, tails, like 100 things, and the parameter is probability of heads is p, probability of tail is 1 minus p. And then, as we derived earlier, the probability you win, the realized probability can be written in this way. It considers this in one formula can take care of two cases, 1 and 0 at the same time. So if you are interested, try what happens if you plug in 1 and then when you plug in 0. See what happens. And then you keep multiply this probability. You multiply the probability from 1 to n. So if you toss a coin 100 times, you have to multiply 100 probabilities that you win. So then in the end, it takes this form mathematically. And multiply from 1 to up to n. And then this is the likelihood function. This is the likelihood function after multiplication of n probabilities. But it is very difficult to handle, so we take the logarithm. If you take the logarithm, then it simplifies this way. So, and now we are maximizing this, which is equivalent to find the first order condition and making it equal to 0. First order condition is pretty simple. It equals to 0. So you have to solve it for, you already have the observations of y. So you only need to solve for p. Solve for p, and then in the end, p equals y bar, which is the sample mean of heads and tails. How many heads you obtain from 100 trials. That is your estimator. So in the end, after the maximization, the estimator is the natural estimator. If you toss a coin 100 times, and if you get 60 heads, then the MLE estimator for the probability is 60 out of 100. The natural estimator. So which is natural, literally. The MLE should be the best estimator. So in this simple case, it has to be equivalent to the intuitive, straightforward estimator like this. So if you want to study the MLE a little more with mathematics, then think about this example again. And it's a natural estimator, and it has many nice properties, and the inference can be done in the same way. Say, for example, confidence interval can be calculated using plus minus 1.96 standard error because it is normally distributed. We know that the MLE is always normally distributed if the sample size is large enough. So you may apply the same inference methods we used for the regression models. So it's also very nice. And also it explains the same thing. Most efficient estimator. It has the minimum standard error, so will be the ideal and optimal estimator in whenever it is possible. Whenever you can do the MLE, that's the best. So that's the simple theoretical lesson, like high conclusion from the theory. And I will skip that. So it I don't know why it is explained now. Later, I will maybe have a chance to explain this. Okay, I am going to call this a video and we'll continue to the next slide and the next one. So thank you for watching. See you later.